Hi, I'm Karen with the Gaithersburg Community Museum. Welcome to International Observe the Moon Night. Tonight, we would normally have been at the observatory, but under the circumstances, we wanted to still celebrate the moon. And we will have a wonderful talk tonight from NIST Physicist John Woodward, who's been working on a project to measure the light from the moon. Before I turn it over to John, I just want to acknowledge that this is a re-recording of the earlier talk, and I want to thank everyone for their patience, especially those people who managed to make it all the way through. But I promise you the sound will be much better this time. So I'm going to turn it over to John. Welcome, John.
Thank you, Karen, for that kind introduction. It's a real privilege to be here tonight and to get to speak to you all. I am John Woodward. I am a physicist at the National Institute of Standards and Technology here in Gaithersburg, Maryland. And I get to talk to you here for Observe the Moon Night. And before I get to the real presentation, I just wanted to say that fall is a wonderful time to be out stargazing or observing the moon. Gets dark early. It's still warm out. Makes for a great night. Get a nice crisp night with a clear sky. It's wonderful to see. The moon's out this week, and there are a few planets up there that you'll see as well. And it's just a really great time of year to get out and observe the night sky. I'm going to talk about measuring light from the moon, and thought I'd start with just a few facts about the moon. The moon is the Earth's only natural satellite. It's approximately 385,000 kilometers or 240,000 miles from the Earth, but of course the moon's orbit is an ellipse and not a circle, so it changes a little bit throughout the orbit. 24 humans have visited the moon, and 12 of them have walked on the moon. The moon takes 27.3 days to go around the Earth, but there are 29 and a half days between full moons. So I'll just pause for a minute to let you think about that and why that might be. And the answer, of course, is that while the moon is going around the Earth is going around the sun. So when the moon gets back to its same position around the Earth has moved with respect to the sun, and takes a couple more days for the moon to kind of catch up and again be on the far side of the Earth from the sun and be full again. The same side of the moon always faces the Earth, and we'll see that in a video coming up. The moon's orbit around the Earth is inclined 5 degrees to the Earth's orbit around the sun, so the orbital planes are a little different. The moon, of course, doesn't create its own light. It reflects light from the sun, and the reflectance of the moon is extremely stable. So most things that humans have put up into space, their reflectance changes pretty quickly when it gets up there. There's a lot of solar damage to the surface, a lot of high energy particles and stuff that degrade the surface. But the moon's been up there for billions of years. So its surface has kind of seen it all, and it's degraded as much as it's going to degrade. So at this point, its reflectance just does not change. And that's useful for us because we want to use the moon as a calibration source and know that its reflectance isn't changing. So I'm going to play a video from NASA, and the video shows the kind of a time lapse of the moon is viewed from the Earth, and you'll see kind of what you expect, which is that the phase of the moon changes. It's half moon, and then now going towards a new moon, and then it'll start brightening again. But you'll also see that there's a little bit of a wobble to the moon. So I said that the same side of the moon always faces the Earth, so you're generally seeing the same side. But as I mentioned, both the orbit's not quite circular and it's inclined with respect to the Earth. So sometimes you're seeing the moon a little bit more from on top, or a little more from on bottom, or a little more from the front or the back as it goes through its orbit. So it has this kind of wobble, and that's called libration. And the libration also changes the amount of light that we see from the moon. So when we're making our measurements of the moon, we need to take measurements both at different phases and different librations to build up a model of how the light from the moon changes depending on kind of where the observer is and where the sun is. And in fact, it takes several years of observations to build up that entire good database to build that model. Here's a little GIF of the moon and the Earth is viewed from a satellite called Discover. It's parked between the Earth and the sun, so looking kind of looking back at the Earth from the point of view of the sun, and what we see is a day there was an eclipse, and the moon moved between the Earth and the sun. And what I find most interesting about this GIF is that while I think of the moon as being pretty bright white with a few dark splotches on it, when compared to the Earth, it's actually pretty dark gray, certainly much less bright than the clouds, and really, not the bright white that you think of when you look out at the moon on a full moon on a clear night, and it's really just a matter of your visual perception that against the dark sky, the moon looks bright white, but when you compare it to something else, it turns out that it's actually pretty gray. It only reflects maybe 5 or 10% of the light that hits it. So I'll just mention a few things about light, since I'll be talking about it throughout the talk. So the visible light that we see with our eyes is really just a small slice of the electromagnetic spectrum, and the part that runs from about 380 nanometers down at the violet end to about 780 nanometers up at the red end. There's plenty of light that you can't see, so the ultraviolet down below 380 and the infrared above 780. And we will measure light both in the ultraviolet and out into the infrared. But light's really just the same thing as X-rays and gamma rays and radar and radio and television waves. For those of you who are younger, there was actually a time when television came through a wave through the air as opposed to out of a cable from your wall. So much the way a phone works now. It's kind of interesting. When I grew up, a phone came through a cable in the wall, and your television came through the air. Now it's the opposite. So to measure the light, we use what's called a spectrograph, and a spectrograph disperses light into its different wavelengths using a prism or a grating. Ours uses a grating, and then it collects them on a detector. Focuses them down onto what's a CCD, which is similar to what's in a camera. And at NIST, we have light sources with a known amount of light that we can use to calibrate our spectrograph. So when the CCD sees the light, it produces a result in kind of numbers of electrons or numbers of counts. So your CCD says, I got 1,000 at 500. Well, what's 1,000 mean? Well, we know how much the spectrograph is looking at. So then we can say, oh, now we know what 1,000 means. 1,000 means, however much we put into it. We can use that to calibrate the spectrograph and then know in actual physical units how much light the spectrograph is seeing. So that's a big part of the kind of thing we do at NIST is to calibrate all kinds of different instruments. The other thing for our spectrograph is to characterize its behavior as well. So we've put a lot of effort into that in order to make these measurements. So I'll tell you a little bit about the idea behind our measurement. The physics lab public affairs people made a nice picture of a solar-looking instrument that I'm going to use. So for the moon, we just have a bigger telescope on the front, but you can see the telescope looking at the sun, and then the light going to something called an integrating sphere. And an integrating sphere is really just a hollowed-out piece of Teflon that's kind of bright white and scatters all the light around inside. And then we take an optical fiber and take that light and feed it into the spectrograph. The same idea for the sun we use for the moon. We just put a bigger telescope on there, and then we put it on a mount so it can track the sun or the moon through the night sky and take our measurements. So here's one of the early versions of our instrument, and you can see it's a fairly modest telescope by scientific standards. It's kind of a nice amateur telescope, 4-inch refracting telescope that focuses the light down into the integrating sphere, which of course is a black cube at the back of the telescope. You can see there in the top image. And then an optical fiber that runs the light into our spectrograph, and then the kind of black and red thing is the mount that tracks the moon through the night. So that's nice, and we so really in terms of the equipment, the hard work is back in the lab characterizing how it behaves. But the equipment itself is stuff that lots of amateur astronomers buy off the shelf and use for stargazing. We don't need a big observatory or anything particularly fancy in that realm. So no talk about astronomy or stargazing is complete without a mild harangue about light in the atmosphere. So this is a picture I took at Mount Hopkins in Arizona. And you can see Mount Hopkins in the middle there with an observatory on top. And so it's a time-lapse picture, about 20 minutes or a half hour. And you can see the star trails, but you can also see a whole lot of light behind Mount Hopkins, and that's because Tucson is behind Mount Hopkins, and Tucson is putting out a lot of light, some of which goes up into the night sky and then scatters around. So that's not great for astronomy, but it's also an indication of a problem we have with our measurements, and our problem isn't the light pollution from Tucson. Our problem is that the same thing's happening to the light from the moon as it comes down to our telescope. Some of it gets scattered in the atmosphere and doesn't make it to our telescope. It goes somewhere else. But we want to know how much light was coming from the moon up above the atmosphere. So we've lost a bunch of it on the way down. And a big trick in measuring the light from the moon is trying to figure out how much you lost, how much light you've lost in the atmosphere. And I'll just say, kind of everything in the atmosphere scatters light, from the individual molecules of oxygen and nitrogen to pollen and smoke and dirt and dust and clouds, ice crystals up in there, all kinds of stuff. So, but the kind of the higher you get, the more of that's below you and the less of it's above you. So when it comes to solving this problem, there are kind of 3 possible solutions. And one of them is to go to a tall mountain and get above some of the atmosphere and then make some measurements of the atmosphere to help you correct for the rest. And kind of another way you could go is to put your instrument on a spy plane and fly it above 95% of the atmosphere at 70,000 feet. And then you'd only have a little bit of atmosphere left you needed to correct for. And it's kind of the easy part of the atmosphere because 70,000 feet, you're above all the smoke and dust and junk that people make down at the surface, and you're above most of the clouds. And the last bit of atmosphere is actually relatively simple compared to what's going on below. And then the third way you could go is you could put your instrument on a satellite so that there's no atmosphere at all. So those different ways have some advantages and disadvantages. The nice thing about being on a mountain is that you can go and visit your instrument anytime you want. You can work every night. If something breaks, it's easy to fix. You can go and calibrate it up on the mountain. You can get it and bring it back to the lab and calibrate it. So it's very easy, and you can put it up there for 5 years and make your series of measurements of different phases and librations of the moon and get a big data set. So that's a great way to go, and we've got a project to do that I'll talk about in a sec. Number two, problem with being on a spy plane is that it's, once the plane goes up, it's up there all alone. You can't, something goes wrong, you got to bring it, got to scrub the flight and bring it back down. It's, of course, a little bit of a harsh environment to put your instrument on a plane and make sure it's still doing what you want. At 70,000 feet, it's about 40 or 60 degrees Celsius below zero. There's not much air, so your electronics don't work very well. There's a lot of kind of engineering that goes into that. And then, of course, a satellite is a whole other ball of wax. Clearly, you're once it goes up, you're never getting it back. So whatever you do to calibrate and understand your instrument on the ground, you better hope that it all stays the same while it's up there. Or you have some other trick up your sleeve. We don't do any satellite work, but there's some smart folks at NASA and other places that do. So really, actually, all three of these possible solutions are ways that people are approaching making these measurements. So going up on a mountain. So the mountain that we're going up is the Mauna Loa in Hawaii. So NOAA, our sister agency, the National Oceanic and Atmospheric Administration, also in the Department of Commerce, has an atmospheric observatory on Mauna Loa in Hawaii, and it's probably most famous as the home to the Keeling Curve. It's where Keeling made his measurements of CO2, and those measurements have continued to this day, showing that the amount of CO2 is growing in the atmosphere. Not a concern for this project, but certainly a concern. The nice thing about being at the Mauna Loa Observatory is there's a lot of instrumentation up there as part of the observatory that measures the atmosphere, and we can take advantage of some of that to know about the atmosphere above our instrument while we're making our measurements. So that's a wonderful collaboration. It's also 11,000 feet plus up above sea level, so you've gotten up above a third of the atmosphere, and the air above the mountain generally hasn't mixed with any of the air down below on the island. So it's been coming across the Pacific Ocean for thousands of miles without a whole lot of human interference. So it tends to be very clear air, which is very helpful for our measurements. So we were out a couple years ago to do some testing to see if the site wasn't, in fact, as wonderful as we hoped it would be, and the answer was yes. There's my colleague Steve Maxwell, who's leading the project there on the left with the telescope on a little platform that we set up on the mountain. There it is running at night. It's looking at the moon, and you can see all those stars in the background and not a whole lot of scattered moonlight, which is really wonderful. It's a sign that the air is clear. If you, go out here in Gaithersburg or most places down near sea level on a moonlit night, the light from the moon washes out a lot of the stars from all the light in the atmosphere. But the Mauna Loa site is really wonderful, and if life were a little different, we would have an operating observatory there now, but we have not been able to get back to Hawaii, but hope to soon, and set up a longer-term observing mission for 5 years that will take measurements of the moon at different phases and librations, and hopefully give us a really nice full data set. So the second thing I talked about was putting your instrument in a spy plane and flying it up to 70,000 feet. And in fact, that's also happening. So NASA has what's called an ER-2 plane, and it's kind of a civilian version of the U-2 spy plane. And it's got these wing pods that you can put instruments in. And if you look at the photo, you can see there's a little slot the instrument can look out of. Most people like looking down at the Earth, but the pod can actually flip around and look up at the sky. So we can put our telescope in the wing pod and put our spectrograph in the middle of the pod where it's slightly pressurized and temperature controlled. But it's a lot of engineering to take that system and put it into the plane. It's got to run off the plane power. It's got to be basically autonomous. You got a few switches that the pilot flicks that tells the instrument we're taking off now, or we're up at altitude and you should start looking for the moon. But other than that, it has to run completely on its own. Like I said, the telescope's at minus 60 degrees. The mid-body, they keep slightly pressurized, but we had to build a container to put all the instrumentation in. And then there's a tracking system that needs to find and point the telescope at the moon all by itself. No help from us on the ground. So fortunately for me, I've got a whole bunch of wonderful colleagues who are great at various kinds of engineering and have helped make this possible. So I'm going to show a little video that the physics lab public affairs people made about the project. And there's no sound, so don't worry about not hearing anything now, and I'll be quiet while it runs. All right, so that's the idea. And here is the reality. So the project is called Air Lucy. This is a picture of the instrument in our lab at NIST. If you look at the picture on the right, in the foreground is the telescope that's on its mount that will help it point at the moon when it gets into flight. And then you can see a whole bunch of cables running back to a big aluminum box on the table behind it. And then if you look at the photo on the right-hand side, that box is in the foreground. And that's what we call the environmental enclosure. So the environmental enclosure sits in the mid-body of the plane. It's got the computer and the spectrograph, the LED source that helps us maintain the calibration when it's in flight, and a whole bunch of electronics in there. And they need to stay warm and pressurized, so they're in that environmental enclosure. And then there are a whole bunch of cables that run out through a bulkhead panel to the aft body, which is completely open to the atmosphere as the plane goes up. And those collect the light from the telescope and provide power to the pointing system and collect all the data. So that's us in the lab. And then we took that all out to NASA Armstrong Flight Research Center in the desert near Palmdale, California, a little north of Los Angeles, where the ER-2 plane spends most of its time. It's its home base. And so this was very exciting, very fun to be out on the flight deck and in the hangar with the planes, and get this guy installed into the wing pod. And you can kind of see over the top of the instrument enclosure, people starting to look inside the wing pod and figure out how we're going to get that guy in there and all hooked up. And then here's a picture. So now we have the environmental enclosures in the pod there on the right, and you can see the cables coming out to the telescope. And there's Steve Grantham doing a few final tweaks before we stick the telescope in the aft body pod and send her on her way. And now we have a YouTube video that the NASA public affairs people put together.
Air Lucy stands for the Airborne Lunar Spectral Irradiance Mission. What we're measuring is the amount of light at various wavelengths that are being reflected off the moon. We want to know this because we essentially are using the moon as a benchmark so that Earth-observing satellites can turn and look at the moon and set the scale on the amount of light they're measuring from the Earth. So it's kind of an indirect way of actually improving our understanding of the Earth.
Both computers are up and running. Artemis has given us a power on. Okay, so now we're going to start logging data. So it's sending code to Artemis.
So we've set it up here even before we put it in the plane. We have a system that simulates it being in the airplane so that we can test it all out. In the distance, you can see a disk of light. That's our moon simulator that we use to calibrate the telescope. We measure the moon's brightness by using a spectrometer, which is actually taking light from a telescope that is pointed at the moon. What typically becomes a problem is that you have to contend with the atmosphere. The atmosphere actually affects our measurement greatly. And so we have actually put that type of instrumentation on the ER-2, which flies up to 70,000 feet and gives us a viewpoint of the moon above 90% of the atmosphere. Almost the same view of the moon as Earth orbiting satellites would have.
Okay.
It's showtime.
In a minute, he'll flip the switch.
Earth observing satellites, we try and calibrate them before they go up, but the calibration always changes. They slowly degrade being in the space environment, and they currently use the moon to trend that degradation. But if we could put a good absolute calibration on the moon, that would allow them to do an improvement on their current calibration scheme, and it would also allow them to intercompare well.
Okay. Success.
So there are a lot of benefits to having all the Earth observing satellites have this common calibration source.
Every instrument that's been launched into space that looks at the moon can benefit from this, because knowing what the moon is, and since the moon doesn't change, helps us both in the future and retrospectively. And then we get much more consistent time series of the Earth.
All right. It was very exciting to be part of. We may not have looked as excited as we were at 2 in the morning there when we got the word that everything was working and we were collecting data. But big sigh of relief and a lot of fun to be out there collecting data from the plane. And just a great team at Armstrong to be working with. And then this slide shows the spectra we collected during what were called our demonstration flights. We were funded by NASA to develop the instrument, and so part of doing that was actually demonstrating that it worked in the plane. So we had 5 nights last November, and got good data on all the nights. We started 10-degree lunar phase, so just 10 degrees past the full moon, so I had a pretty bright moon to look at, and then got less and less light every night as the moon worked its way down to 59 degrees phase, so a little more than half full. The nice thing that I see in the data is what I don't see in the data, and I don't see big absorption lines from water or from oxygen that you usually see if you're looking from the ground. That kind of means that the effort of flying up at 70,000 feet paid off. We don't have much atmospheric correction that we need to do. Things look good, and we're hoping to get more flights in the future. Of course, that's all on hold as well, but we're excited about continuing. So I just want to acknowledge some of my colleagues. So Kevin Chirpy is the PI on the Air Lucy project, and Steve Brown and I are co-PIs on part of the NIST team. Steve Maxwell is the lead on the Mauna Loa work, and Steve Grantham and Tom Larison and Clarence Arabia have been doing a lot of the engineering on making this all work. Joe Rice and Jory Frazier have been wonderful leaders and very supportive of the work, and that's been really great. So Tom Stone at USGS, he's the guy who runs the model of the lunar irradiance, and all this data will kind of flow to him so that he can incorporate it to make a better model. Andrew Gadsden and his graduate students, Andrew Cataford and Andrew Newton, put together the tracking system that kept the Air Lucy system pointed at the moon while it was in the plane. And then Brian Hobbs, Fran Becker, and Tyler Latcha have been our contacts at NASA Armstrong and kept us on schedule and in the know about everything we needed to do to get the instrument flying in the plane. And Marty Martinson's been our contact at NOAA and has been great to work with in terms of trying to get everything set up there. All been just a wonderful group of people to work with. I thank you so much for listening to what I have to talk about tonight, and I hope that if you have any questions that you'll type them into the chat or get in touch with the museum, and they will forward them to me, and we will get answers to you. Just like to thank everyone again for the opportunity to talk.
Thank you, John, for that fascinating talk. It's really incredible to explore the moon, and even though we weren't able to do it in person at the observatory, having this virtual program was a great benefit for all of us. I also want to say that usually we have some hands-on activities, and if you look down in the Community Museum Facebook feed, we did share 2 moon activities that I hope you will be able to do. And even though the weather has not cooperated with us tonight, please take the time over the next few days to go out and observe the moon in person. Thank you.